All right, so I'll be kind of going through some review today. So my first section, I did a lot of the problems off of practice exam A. Obviously, I'm doing a lot of the work on the board, but I kind of have the audio or the recorded version up on YouTube page. So you'll have two different versions. We're going to work through practice exam B. Now I've got the answer keys up there on Canvas, so you can kind of look through both of them. I might even change things a little bit that I think might be a little more helpful for the exam next class. If you're working through that Excel assignment, I mentioned this the other section, gotten some last minute emails. If you're confused on 1B, that's why I said work on it a lot earlier. That goes all the way back to when we were using that Indiana weather data file, right? If it's using that norm.dist function, it's going to tell you the area to the left of different cutoff values, right? And then 2 and 3 are going to be the confidence interval stuff that we did on that YouTube file, YouTube likes or dislikes file. Unless there's any questions that anybody has specifically on these practice exams, I'll probably just kind of pick and choose which ones I think would be the most helpful to kind of know going into this. I'll also mention, I thought I deleted these, some questions that were on these practice exams that I didn't. So anytime you see something about critical values, I think I mentioned this, you can just ignore those, right? I apologize for the life stuff that's kept me out of class a little bit recently. And so I usually go over a kind of additional topic for this exam, which is critical values. Because I wasn't able to kind of go through hypothesis testing as much in person, I want to kind of just hold off and just do p-values for this exam. So ignore the critical value stuff. I had these written up early, and so I thought I went through and deleted them before I posted them, and I realized I have. Okay, so don't worry about the critical value questions. Okay. Any specific problems people want to work through? Otherwise, like I said, I'll probably pick and kind of choose here. Yeah.
I don't know all of it, but it's like finding the t-table.
So come back to that, because I will do one of those. That was the second thing I was going to do. So any other questions other than that? If anyone okay, so I wanted to make sure I went through some really old stuff first, just because it's been really far removed, and it really should be some of the more easy questions on the exam if we've got a kind of nice refresher of it. So if you go all the way back to at end of the last exam, we were talking about uniform distributions, right? So these uniform distributions were where we were thinking about there's just some variable, and every value in between the minimum and the maximum are equally as likely. So we kind of have this flat distribution, kind of called that maximum value D and that minimum value C, right? Just kind of notation. So here I've got this uniform distributed variable. The minimum is 15. The maximum is 75. So just like the other exam, my formula sheet walks through things in the order in which we covered them in class, not from left to right. So it's down the left column, then back up, and then down the right column, right? So you should never be using stuff in the bottom right column for the first couple questions. I mean, just making it easy for it, right? So we've got this set of equations here, which is our uniform distribution equations, right? So here's how we find the mean and the variance of a uniformly distributed variable. So the mean, we're simply looking for that middle value, right? Everything's equally as likely, so we're just looking for the middle value in between the minimum and the maximum. If I want the middle value in between two values, what do? I just add those up and divide by 2. Here, my maximum and minimum, we're kind of using D and C. So add those 2 up and divide by 2, right? So here what? 75 plus 15 divided by 2. I think it should be 45 if I'm doing that in my head correct here. Okay. Excuse me. So all I'm doing there, that should be a very easy question. Like I'm hoping that it's kind of like when I asked you to find a mean on the first exam. Hopefully everybody gets this one right, right? Now, if I ask you for a variance, right, how do I find that? Well, once again, I've got this formula sheet, so I'll give you the formula sheet, Z tables and T tables in the exam. I've got this in front of me. It says take the maximum, subtract the minimum, right? Look at that range, okay? So here, look at that range of possible values between the maximum and the minimum, so maximum minus minimum. Square that and divide by 12, right? Where does that 12 come from? Remember, we skipped the mathematical proof, but if you walk through the mathematical proof of how you find the variance, you can simplify the equation down to it's always gonna be the range of values squared divided by 12. So think if I do this one, I get what? Some nice number. Did I ask you for the oh, this is A. Sorry, we're looking at B, aren't we? My guess is this is 300. I'm doing the math in my head correct there. So I've got a variance of 300. What if I wanted the standard deviation? What's the only other thing I'd have to do? Just take the square root, right? So make sure you're reading carefully if I ask you for a standard deviation of variance. So the next kind of thing I could ask is, okay, what's the probability? So this is the amount of time we're waiting in line for what? The roller coaster. So this could be any, this could be the amount of time you wait at a grocery store or anything. Right? So what's the probability that we wait for more than 50 minutes? Okay. With a uniform distribution, I'm just looking for the area of a rectangle. And in fact, here, before I even start to go into how I do this, what do I know that probability has to be less than? Yeah, 0.5. Right? So why? Because the mean with a normal and a uniform distributed variable, they're symmetric. So the mean exactly splits it in half. There's 0.5 to the left, 0.5 to the right. I want something that's a little bit smaller than that. So right away, from looking at these, I know it's C or D, right? Now, to actually find the exact value, the way we find the height of a uniformly distributed variable is just 1 over the range, right? Or 1 over the maximum minus the minimum. And the formula sheet kind of reminds us of that right here. If we're within the range of possible values, in between the minimum and the maximum, the height of that distribution, or the probability, is 1 over that range, 1 over the maximum minus the minimum. So here I've got what? 1 over 60? Then it just becomes, I'm finding the area of a rectangle, right? Now I'll show you that you can use the formula, right? If you want to actually find the probability between the two values, you could use this. But I think it's easier if you just draw this out. I've got the area of a rectangle. What's the height of that rectangle? 1 over 60. What's the length of that rectangle? Well, it goes from 50 to 75. So times 25. I'm guessing this is 0.42 if I get this out of my calculator. Any questions on that? Now, if you really wanted to, what you could have done is say, okay, here's an equation where if I know I'm looking for the probability in between two values, I can use that equation, right? That B minus A over D minus C. Well, all that's really saying is, where does my interval start and stop, right? Well, it has to stop at the maximum. So it would be 75 minus 50, is what we did to find 25, and then divided by my maximum minus my minimum. Dividing by something is the same as multiplying by 1 over that. So like I said, you can plug everything into that equation if that makes more sense to you. I think it's easier to draw it out and just think about this is the area of a rectangle. As long as I know the height is 1 over the range or 1 over the maximum minus the minimum, shouldn't be too bad there. Okay. Any questions on that? Or I keep going here. Got one more thing with a uniform distribution. It's a little bit different than what I've got in problem 4. So I'm going to change it a little bit from this example, this practice exam. So I'm just going to draw this out again. So let's say instead, I asked you, what's the probability you wait in between 20 and 25 minutes, or you wait in between 60 and 65 minutes. Okay. So I've got 2 different rectangles that I need to find. Okay. Well, hopefully, like on the exam, if I ask you 2 questions like this, like if we got the height of the distribution, we can kind of keep using that, right? It's not going to change. I haven't changed the value. So I've got the height of this distribution is 1 over 60. So if I want to find the area of this rectangle, the height is 1 over 60. What's my length? It's going from 20 to 25, so just 5. So 5 over 60. Now, I wanted the probability of being in between these 2 values or in between these, so I need to add those 2 areas together, but I don't have to do any more work. what's this probability gonna be? Being in between 60 and 65. Same thing, right? Equally length sized intervals have the same probability of occurring for the uniform distribution. So I've got an interval of length 5, just like I did before. I could rework the whole thing and do it again, but I'm just gonna end up with another 5 over 60, right? So I get what? I think if this simplifies down to whatever 1/6 ends up being, or 10 over 60. Any questions on that? So that there's practice exam, I just asked you for the find the probability between like two values here. I could ask you the probability in between these two or these other two, and then it's just adding them together. And quite often, I wrote the exam, so I quite often keep the intervals the same length, so that if you know that principle, it makes it a lot quicker, right? You know it's going to be the same probability. Yeah. You're good.
You get that 5. I wanted it.
Yep, so if we're looking for the area of this rectangle, right, we know the height is 1 over the range. The length is just gonna be, well, what's the length of whatever two values are in between? 20 to 25, 25 minus 20 is 5. Yeah. Yeah, sorry, I didn't write that math, I got thinking too fast. Any other questions there before we keep moving? So like I said, I just wanted to kind of refresh us on that uniform distribution because these really should be some easier questions, right? I'll be completely honest. I expect on average, not as many of you get the hypothesis testing stuff correct, right? But if you come in prepared, you get these earlier questions that are a little bit easier to correct. It's going to help you out quite a bit. So we're going to go down because I had a question about this, and this is what I wanted to do. We're going to go to question 15, all right? So we're going to do confidence intervals and hypothesis testing. So these practice exams, I try to set up very similar to how I'm going to do these exams, right? So I'm going to give you a bunch of information. I say use it on the next 5 questions, right? So we're going to keep using all this information as we go from the confidence interval questions to the hypothesis testing. So for my confidence interval questions, I've got here, I want the 90% confidence what the true population mean IQ is. I took a sample of 49 students. I see they have a sample mean IQ of 109, and I somehow, whoops, this is the wrong one. Hold on. I wanted to do a sample variance one because that's what you were asking, right? Well, actually, yeah, let's just change it. It'll be different from the practice exam, but that'll be good because then you'll have the practice exam answers and then you'll have what we do in class. Okay? So I'm changing this one. Instead of having a known population standard deviation, I've only got a sample standard deviation. Okay? So how's that going to change things? So before we get into this, something that's really good to have in mind going into the exam, if we're doing confidence intervals or hypothesis testing, anytime we've got a known population variance or a known population standard deviation and we're looking at sample means, we know we can use that standard normal or the z-tables. Or if I'm ever looking at examples where I've got sample proportions, right? And, I try to make this, I use the terminology. So like up here, I've got what? You've got a, sample proportion. I even try to use the notation of p hat so that you can kind of match it up to the formula sheets. Anytime we have one of those two scenarios, we'll be using the standard normal tables. If we've got a sample mean, but we only have a sample variance or a sample standard deviation, right? Because if we know the variance, we inherently know the standard deviation, then I'll be using that student t distribution. So here, because I changed this example, we only have a sample standard deviation. So let's just kind of write down some of the things that we're getting. Okay? So we want this 90% confidence interval. We've only got a sample standard deviation, so we know we need to use that student t distribution. And in fact, even on the exam, I probably will do something like this. Be a little bit more intentional to like really let you know, like this is either a sample standard deviation or a known population standard. Okay. So I've got the standard deviation, what was it? 15. I found a sample mean of 109, and I had a sample size of 49 students. Okay. So I want this confidence interval. I go to my formula sheet, and I tried to kind of group them really nice. Okay, we have 3 different types of setups, right? 3 different types of confidence intervals we could do. Sample mean where we know the population variance, sample proportion, sample mean where we only have the sample variance. And the formula sheet tries to remind me, if it's a proportion, or I have a known population variance, you're really using that z-table. If you've got a sample mean with only a sample variance or sample standard deviation, use that student t distribution. Okay. So from here, it's a matter of getting things plugged in, right? What's my sample mean? 109. Okay. And I'm going to add my margin of error to my upper bound, subtract that same margin of error to my lower bound. Now I don't know the t value yet. We'll do that last. I then multiply it by the square root of, well, I was given the standard deviation, so that's just s, right? So I need to make sure that I'm going to square that value, right? If I'm only given the standard deviation, I need to be plugging in the variance there for s squared. So if I've just got the standard deviation, that's just s. So I need to make sure I'm still squaring it. And then divide by, whoops, I almost wrote an n, the sample size, 49. Okay. So the only thing left I have to do is look up that t value. Right? So what's that t value going to be? Well, when we're looking at that student t distribution, we said we needed one more thing, which is my degrees of freedom. We said this was simply what? n-1 or my sample size minus 1. So here, 48. Okay. Well, what's the area I want in my tail? Well, if it's a 90% confidence interval, and this is where I draw these things out. I think it's probably helpful in the exam. Like just draw out as much stuff as you can. I think it always helps to have a visual. I'm looking for this number of standard deviations away. I need to go to the left. Left and the right to get a total area of alpha outside my confidence interval. Right. So if my confidence interval is 90%, what should my alpha be? So my alpha is going to be 0.1. I've got half of alpha. So I've got half of alpha on each side of my interval. So you're right, the area in the tail that I want is going to be 0.05, right? And once again, these formulas try to remind me of that. Whatever my alpha value is, divided by 2, right? Because you got half of alpha on each side. Okay. So I now know the area that I want in my tail is 0.05, right? And my degrees of freedom is 48. Those are the two things that I need to go to my student t table. Scroll down, I've got what? 0.05 is the area I wanted in my tail. And then I keep going here. And I've got degrees of freedom of 48. So 1.677 is the number of standard deviations to the left and to the right that I need to go. And now it's just a matter of getting this entered into my calculator. Right? I'm never going to try to trick you. Like, once you find the lower bound, I'm never going to give you ones that have the same lower bound or the same upper bound. So you really only have to do the calculation for the lower bound or the upper bound, and then you should be able to identify the correct answer. Right? Just for the sake of time thing. Right? If you really want to, then you can go back if you have extra time and calculate the other one. Now, another thing that I would kind of suggest that sometimes can prevent from making calculator errors is, remember, what this really represented was we were taking our sample mean and going this many standard deviations to the left and the right. We took that many standard deviations and then multiplied it by whatever the standard deviation was. Right? So the standard deviation of my sample statistic here, sometimes it's helpful to just calculate this on its own so that you just have one value to plug in there. Now you can't do it all at once. It's just like I said, it's, there's more moving parts. It's a little bit easier to make an error on your calculator. Okay? This is more like test taking advice, not like you have to do this or that. Any questions on this? Yeah. Yeah, so I have to go back, and probably didn't help that I didn't have the exam pulled up, I think, as I was saying this. But we originally asked for the 90% confidence interval. So remember, we've got our confidence levels. We'll eventually start talking about our significance levels for hypothesis testing. Our kind of three benchmarks were 90, 95, and 99. Sorry. Those correspond to 0.01, 0.05, and 0.01, right? So the way that we found alpha was it's the percent outside my confidence interval in decimal form. So 90%, the significance level or the percent outside is 10%. In decimal form, 0.1. 95%, my significance level is 5%, or the area outside of my confidence interval is 5%, in decimal form, 0.05. And then, of course, the 99 we have. Is that where you're kind of getting at? Yeah. And I'm not gonna, I'll be honest, I'm not gonna like give you a 93.2. I mean, these are our benchmarks, right? These are the ones that we are standard, right? We could do a 93.2, but I'm not gonna expect you to do that. Any other questions before we keep moving? Okay. So I've got my confidence interval. I guess I could use Excel real quick. So we, wait, what, 109 plus 1.677 times the square root of 15 squared over 49. So 112, right, should be my upper bound. And then 105-ish should be my lower bound. You're trying to kind of reproduce these and check this, right? Now, what's interesting is if you look at the actual practice exam where I had a known population standard deviation, that lower and upper bound are going to be a little bit different from that. Why? What's the only thing really that would change here if I had a known population standard deviation? So I look at these confidence interval equations. The only thing that's different, right? Still be plugging in my standard deviation, sample size and sample mean. The only thing that's going to be different is my z values and my t values are a little off. In fact, if I look up 0.05 in that standard normal, I believe that it's 1.645. And you can use that standard normal table, but if we're getting comfortable, another little shortcut we could do is if we want 0.05 in the tail and we had a known standard deviation, population standard deviation, those z table values are in this last row, 1.645. But notice it's a little bit different, so our answers are going to be a little bit off. And how much off are they going to be? Well, yeah, you might say, well, that's 0.03. It's not very much. Well, 0.03 if the standard deviation is 100,000, right? If we're something, we're dealing with incomes, well, this is going to be a pretty big difference. Right? Any questions on that before I keep moving? Okay, so let's dive into some hypothesis testing here. We'll kind of keep using the same setup once again. Our answers are going to be a little bit different from what we're looking at here on the practice exam because I changed the example to only have a sample standard deviation. So we want, in this first one, to identify the null and alternative hypothesis. So I'm going to test for whether or not the average IQ of Ball State students is different than this national average of 105. The sample mean I found was 109, right? I wrote these so you can keep using the same information. You don't have to start with a whole new set of values. So how are we going to find that null and alternative? Well, it's always best to just identify the alternative because that's what you're trying to test for, or that's what you're trying to find. I want to know, is the IQ of these Ball State students, the sample I took, different than the national average? So anytime I see this term different than, I said this in one of the recordings that I kind of posted the week we missed. Different than should always tell you you have what type of tail test? Two-tail, right? Am I different than this value? Another way of saying that is the mean not equal to this national average of 105. Right? So another kind of key here is whatever you find from your sample, that's not the value in your null and alternative, right? That's the value that you're using to challenge that null and alternative hypothesis. So here we found a sample mean of 109, but what we want to test for, what we're interested in is, well, is that sample of students that we found, is that different than or not equal to that national average of 105? The null then is the exact opposite of that, or the complement of that, which if I'm saying is it not equal to 105, the null is that it's exactly equal to 105. Okay. So we know right away we've got a two-tailed test. Okay. Got a not equal to sign. If I see an IQ, sample IQ above 105 or below 105, both of those would just be inconsistent with my null. Right? Evidence on either side is kind of going against that null there. So the next step is we generally then want to find our test statistic. So how do I do that? Right. Well, I go to my formula sheet. Hopefully it can help me out. Sure enough, down here in the bottom right, I've got three different test statistic equations. Just like confidence intervals, they correspond to the three different types of examples I can see. Sample mean, where I know the population standard deviation, it's a z statistic, right? Or it's a test statistic coming from that standard normal or the z tables. sample mean where it only had a sample variance, well, then it's a test statistic coming from a student t distribution, so the t statistic. And then once again, proportions, anytime I see this word proportion, off the t table to the side, I'm always using the standard normal. Okay? So the only time you use that student t distribution is if you only have a sample variance when you're looking at a sample mean. Okay. Any questions? Before I keep moving here. Okay, so I've got only the sample standard deviation of sample variance, so I'm using this guy here. Now notice there's two different versions of this equation. It's just written a little bit differently mathematically. Depends on what information. If I had the sample variance or I had S squared, this one's probably a little easier to use. We could just plug that value in. If I've only got the standard deviation, this one's probably a little easier to use. So I could just, that's just S, right? The standard deviation is just S. So we'll kind of use that one. The sample mean we found was 109. The assumed true mean, well, that comes from my null alternative hypothesis, right? That's the assumed true value up here. So mu subscript 0, 105. And then I'll divide by that standard deviation over the square root of my sample size. If I'm looking here, my guess is this is, well, first of all, which of these could I rule out right away? Yeah, why? Yeah, I found sample evidence that was above the assumed true value. So remember, this assumed true value, if it is in fact true, my sample means should be normally distributed around that value. I found 109, that's going to be a certain number of standard deviations above, right? So it has to be a positive value. So I can rule out the negative ones right away. This is one of those things where, like, if you know the principles, I can draw this out, know that your sample means distributed around whatever value is in that null alternative hypothesis. Now I can boil this down to a 50-50 shot, even if I can't get my calculator to even work, right? Okay. Now on the exam, I'll also mention at this point, if you don't have the null alternative hypothesis right, you use the wrong value, how are you going to get the test statistic right? So a lot of what I'll do on the exam is, if I ask you to identify a null alternative hypothesis, on the next question, if I ask you for a test statistic, I might use something like, say, assume the null alternative hypothesis was this. And I might use a different value from what the previous question was. I might completely change the test, right? So maybe, you know, I ask you to identify the null alternative, and maybe it's a two-tailed test. But then the assumed true hypothesis I give you is maybe a left-tailed test, right? So don't read into the assumed true values I'm giving, right? And I might be doing it for a completely opposite reason for what the actual answer was to the previous problem. I'm just doing it so that I make sure everyone's starting off with the same, I'm gonna have the same quote. You don't have these cascading errors. Okay. But here we've got the answer key. So we know that this is the correct null alternative, so we know that we're working with the right one. So we've got this two-tailed test. The next step is going to be to find my p-value. So I'll usually do something like I did in 18 here, where I give you the assumed true test statistic, right? Similar idea. If I get the test statistic wrong, how the hell am I going to get the p-value correct, right? Or my rejection decision is correct, right? So I'll give you an assumed true test statistic. So I'm going to cheat here for a second. I'm going to change the value from the example. So let's do, okay. So instead of this negative 2.3, let's say I do, let's assume, so this ended up being what, I don't know, this is probably 1.867. I'm guessing. I might be wrong on the math. If I am, let me know. Is that right? Okay. So let's assume that instead, make sure we're all starting off on the same foot, I tell you that test statistic was actually 2.011, right? So we're all starting off with the same test statistic, no matter if we got the previous question right or wrong, okay? The p-value, kind of definition we use, it's the probability I saw sample evidence as inconsistent with the null as I found, or anything even more inconsistent. So for here, if I find a positive test statistic, I'm gonna be looking at the area to the right. Okay? Now the problem is, I can find this using my student t-table, but that's not the end of the story, right? Because seeing something this far away from that assumed true mean, I could have seen something equally as far away on the other side, and evidence on the other side was equally as damning against that null hypothesis, right? So every single value here has an equal counterpart over here that would have went against the null just as much. Now, that's only true for a two-tailed test, right? We'll work through a one-tailed test example next, and I'll kind of, we'll kind of see the difference, right? But for a two-tailed test, evidence on either side goes against the null. We only take one sample, so we can find the area in this right tail. We then have one more step, which is we haven't, equally as likely we saw something on the other side, so we multiply it by 2. Okay. Any questions on this idea before we actually look up what this area is? Okay, so we got our test statistic, that t value of 2.011. Got my degrees of freedom. I erased it from earlier, but we said it was what? n-1, so 48. So I go to my t-table. I've got my degrees of freedom of 48. I go over, I find my test statistic of 2.011. On the exam, I think the other practice exam A, I think it has an example where it gives you one that's not an exact value in the table. Once again, because we had a little bit less time, I'm not going to expect you to do that. I'll give you a value you can find in this table for the assumed true test. So I've got 2 points, where I already lost it. 2.011, right? That was my test statistic. So I'm then just going to go up and see, okay, what area in the tail corresponds with that test statistic? 0.025. Okay. So my p-value here is going to be 0.05, right? Multiplying that by 2. Now, what levels can I reject at? So I think that's even what this original question kind of had, right? What levels can I reject at? Well, I only reject if that p-value is less than alpha. Okay. So I can kind of compare this to 3 different alpha values relatively quickly. I've got 0.1, 0.05, and 0.01 being my benchmarks. If you write this out, I would suggest writing it out for whatever reason. I don't know, decimals that can kind of trick yourself in your brain. Hopefully this is easy to see. Is this value less than this value, right? Is 0.05 less than 0.1? Yeah, so I can reject at the 10% significance level or the 90% confidence level. Is it less than 0.05? This one is a little tricky, but no, it's not less than, right? It's exactly equal, so it's not less than 0.05. So I would fail to reject. If it's not less than 0.05, it's sure as hell not going to be less than 0.01. So I'd fail to reject at that 5 and 1% significance level, and I would only reject at that 10% significance level based off of this setup. Any questions on that? So a lot of times what I'll do here is notice I don't give you the p-value. The real kind of, this is like 2 questions in a way in one, where you have to find the p-value and then compare that to alpha, right? So once I have the p-value, I can then compare it to alpha to make my rejection decision. Okay. Any questions on that one? Okay with that? Sure. No other questions on this type of exam? All right, I think probably best is do another hypothesis testing one. Kind of the newest stuff. Also, we could do the confidence interval portion if we have enough time. So I'm going to scroll back up and let me think if I'll have enough time to do this. I should have enough time. So let's do the confidence interval first, right? So we've got this example where it's a portion of people who own dogs, right? So it's 40% of households own a dog, right? From my sample of 100 households, okay? So I've got this sample proportion. Start writing it down in different colors so we don't confuse this in case anyone's still writing it. So I've got my sample proportion of 0.4. My sample size at 100 households is 100. If I want to build this confidence interval, right, for the 95% level, what's my alpha value? So 95% confidence. Yeah. 0.1 was the previous one, right? We had 95% confidence, 0.05. Okay. So I go to my formula sheet. I look at my confidence intervals, and I even use the notation in the question, right? P hat. And I use the word proportion for using that confidence interval for sample proportion. I'm just gonna start plugging my values in there, right? So I've got what? 0.4 was that sample proportion. And then gonna add to get my upper bound, my margin of error, subtract my margin of error, get my lower bound. I'm not gonna look at my Z value yet, but I'm gonna plug in everything else I know, right? So I've got my sample proportion times 1 minus my sample proportion over my sample size. Once again, this represents the number, this is how many standard deviations away I want to go, times whatever the standard deviation of that statistic is, right? Might be helpful to, calculate this stuff really, so then you just have one value to plug in there. That just kind of prevent calculator issues. So I need to find the Z value that gives me half of alpha in each tail, right? So we set our alpha as 0.05. So half of that, 0.025. Okay. Now I'm dealing with proportions, so I am using that standard normal Z table. I'm going to go up here. I know the area and the tail, so I have to find that value in the middle of this table, then go over and up to find that corresponding Z value that gives me that cumulative probability or gives me that area and tail. So I'm looking through here, it looks like 0.025, that's the area that I wanted. So 0.025, that corresponds to negative 1.96. And once again, as you're working through more of it, like it's always going to be, if I want the 95% confidence interval, or an example where I'm using that standard normal distribution, I'm always going to find the same value of 1.96, right? But that's how you would actually go through and do it. So I got negative 1.96, get my lower bound, positive 1.96, get my upper bound. It's already kind of built into my equation. So the Z value that we needed to use, just 1.96 there. Okay. Any questions on that before we keep moving here? Okay. Let me see. I think there might be something to point out here. I think on this one, I didn't give you any that don't make sense. But if I ever gave you a confidence interval where that 0.4 wasn't smack dab in the middle of that confidence interval, you know that can't be the right answer, right? You're building that confidence interval around the sample portion that you found. Okay. So we're going to use the same information, but we're now going to want to test this hypothesis where we see the media put out this thing that said, what, less than, I'm guessing? So you want to test the proportion, or no, sorry. You want to test the hypothesis that the population proportion of families who own a dog is greater than 36%. So what we're wanting to test for, that's our alternative hypothesis. And we want to know, is that true population proportion of people who own dogs greater than 0.36? We assume the opposite is true for our null, stacking the deck against ourselves. So we've got kind of this greater than sign in our alternative hypothesis. So we have what type of tail test? A greater than or a right tail test, right? So here, only evidence on the right side of the distribution supports the alternative and goes against the null, right? So we think about here, if what we assume to be true was in fact true, and that population proportion was less than or equal to 0.36, if that 0.36 value was the true population proportion, only values that are on the right side of the distribution go against that null, right? Anything on the left side actually supports the null. We don't have to go through the steps. We know that we're not going to reject it. If I find something that supports the null, why the hell would I reject it, right? So we're going to be thinking about our p-value. Once we find our test statistic, is the area to the right, this right tail test, right? So how do we find that test statistic, right? Well, I found a sample proportion of 0.4. Right? I need to turn that into a test statistic. Once again, we're going to skip the critical value questions for this exam. So go down here. Oh, nope, it was on my Word documents. I've got my test statistic equations. Here's my sample proportion. Okay? So all I'm going to do is start plugging in my values. I'm going to write this all out and then plug the values in because I want to use it for something else once we finish this one. So we've got what? 0.4 was my sample proportion. The assumed true proportion was 0.36. 0.36 was my assumed true proportion. That's what I'm using in the denominator. Times 1 minus that assumed true population proportion divided by my sample size. Once again, if you do this all at one time in your calculator, it might make sense to kind of calculate this ahead of time so you just have one value to plug in the denominator. Also, if it was me, if I look at these values and I can do the math in my head, then I don't have to worry about parentheses in my calculator if I know this is just 0.04 in the numerator, right? So little things like that can got to be helpful as well. So that 0.4, so these sample statistics are going to be something that from data we could calculate, but it's going to be something that I actually have to give you. So this is where I'm giving you information with a confidence interval 1, but I say keep using it for the next 5 questions. Yep. So that sample proportion of 0.4 is going to be coming from that previous problem. Yep. Any other questions before we keep moving here? So we plug everything in. I don't know. Let me see if I can guess this one right. Probably not. Where are we at? There we are. Is it 0.833? Does anyone have the answer? Okay, so I think it's, I'm trying to remember what I chose here. So we got 0.833 is that test statistic. If I plug that into my calculator, this corresponds to a Z statistic of 0.833. And remember, the p-value represents the probability I saw sample evidence as inconsistent with what I assume to be true, or something that's even more inconsistent. So I'm looking for this area to the right. So I can go to my table and look up 0.83, right? That's as close as I can get, or 0.833. The closest I can get is the second decimal. So I can look up a Z value of 0.83, right? So this is where we're going to be kind of constrained. So I go 0.83, right? That Z value corresponds to an area of, or probability of what? 0.7967, right? So that's my p-value, right? No, what do I still need to do? The table actually gives me the area to the left, right? So 0.7967 is the area to the left. I wanted the area to the right. I need to do 1 minus that. So I get something roughly around 0.2. Why is this an easy one to make rejection decisions with? If my p-value is 0.2, what levels can I reject at? 0.2 less than 0.1? No, it's not less than 0.1, won't be less than 0.05 or 0.01. I can't reject at any level here. I didn't find sample evidence that was, wasn't very inconsistent with what I assumed to be true. It was only not even a standard deviation away. So it's very likely this could be the true proportion, and I just happen to see a sample that was a little bit further on that right side of the distribution. Okay. Questions on that? So on the exam, I think the practice exams have it split up, but I'll probably tell you a little more like it. You might see a hypothesis test of each type, right? We worked through ones today where I had a sample mean and an unknown population variance. I just had a sample variance using that student t distribution. I might ask you one with a proportion, right? Use the Z tables. The one we didn't do is if I have a sample mean and a known population standard deviation, but that really is just a slight, the test statistic equation looks very similar to the first example we worked through. And then using the Z tables for that type of problem would be very similar to this second question that we worked through, which is kind of why I chose to do those two as opposed to the third one. Right? One other question, this might be like my separate the A from the B's question, would be something like, let's say, and I think this might be, let's see, did I put this as a question on here? Might be down here. No, I didn't. It's on practice exam A though. So you'll have another version of what I'm about to do on practice exam A. Let's say we had this household example for dogs. And I said, okay, look, assume that instead you found the same sample proportion, but it was from a sample size of 200 homes, right? So your sample size is higher. Which of the following is going to be true? And I might give you statements about the test statistic, the p-value, and then are we more or less likely to reject the null? So if my sample size goes up, what's going to happen to this fraction here? Remember, what does this represent? that standard deviation of whatever sample statistic we're looking at. So if my sample size goes up, what happens to this thing? Fraction. Larger denominator, my standard deviation gets smaller, right? So kind of write out the implications, right? So my sample size gets higher, that standard deviation is going to get smaller. If my standard deviation is smaller, what happens to my test statistic? Well, I've got a smaller denominator dividing by a smaller number. My test statistic, whether it comes from a standard normal or a student t, will then get higher. And I kind of already erased this a little bit, but I think what we had before. Right? If my test statistic is greater, right, or higher, what's going to be true about my p-value? I'm moving this test statistic out. What's happening to the area in this right tail? It's getting smaller, right? So my p-value is smaller. And if I only reject when the p-value is less than alpha, is it more or less likely I reject the null? Well, if that p-value is getting closer and closer to 0, it's going to be more likely it's less than these alpha thresholds I've set. So kind of the end result, and I may not ask you to identify every single step, you know, the question may not be asking about every single specific thing. You know, going into it, even I would remember, you know, just having a greater sample size, more likely we can reject the null. Smaller sample size, less likely we can reject the null. Right? Kind of moving the same direction there. But this is the reason why, right? We follow the kind of chain of events. It's because having a higher standard deviation reduces having a higher sample size reduces the variance or standard deviation of my sample statistic. Having a smaller variance then increases the number of standard deviations away that sample evidence was, or increases that test statistic. Higher test statistic, smaller p-value, more likely we can reject it. And if I do ask you a question like that and you want to work through it, like if I give you 200, if I had time, my suggestion would be, if I'm asking you like, okay, what happens to the test statistic? Calculate the test statistic, right? Plug in 200 instead and just see what happens to it, right? I mean, you can reason through it without any values, but if I'm giving you a new sample size, just use that, find the new test statistic. If you're not even sure that the higher test statistic leads to a p-value or a smaller p-value, look up your test statistic in the z-table, figure it out. Oh, it is a smaller p-value, right? But you can do that without any values as well. If you want to, you can kind of reason through it there. Any questions on this? Like I said, this will probably be like toughest thing I would ask on the exam, right? May even be a bonus question. So any other questions kind of about the logistics of the exam or anything else that you kind of have a question on? So before I let you out of here, the other thing I would mention, if we go back, kind of the stuff that we didn't get to in class, don't overthink it. It goes way back to what we were doing when we just started out with a normally distributed variable, right? So we didn't have to worry about all this sample mean stuff, right? I'm going to have a couple questions in there where it goes back to, I'm just starting out. I know the population mean, I know the population variance. Everything's nice and easy. I can just calculate these z values and find the area to the left or the right. So this goes all the way back to like early problems on that Connect homework, right? Then I might ask you simply, okay, you know what the population mean is, right, in the previous problems. Now assume you take a sample, and then it's just a matter of we're calculating z values for a sample mean, but we were given this known population variance and population mean. So it goes back to, we can use this z-value equation, then it's just looking up those z-values to find the area to the left, the right, or in between. Okay. So on Friday, I'll bring t-tables, coordinate sheets. I do have a section that's right before this, so might try to give them a little bit more time, an extra 5 minutes before I let you guys in. I'll do the same for you. Other than that, office hours today, 3 to 5, and tomorrow 3 to 5, or sorry, 2 to 5 each days. If you have last minute questions on the Excel assignment or questions on the exam, feel free to stop by or send me an email. Okay. All right. See you guys on Friday.
Yeah.